All right, so I would suggest we start by visiting very quickly, the semester calendar. So if you take a look at the lecture site, the semester calendar. So we are basically the week right before the reading week. So we are now in lecture number 10. So today we're gonna dive deeper into the graphs by introducing more terms, especially trees, forests, spanning tree, etc. We're gonna do that, and then we're going to talk about graph traversal, which is kind of a fun topic. Today, it's not going to be very algorithmic, but I just want to talk about the basic concept about some traversal. But we'll do some illustration, some example as well. So please notice that by Monday next week, I will release your assignment number 1. And then it will be due on the Wednesday after your reading week. So you got about 10 days or so to actually submit the assignment. Of course, after that, I'll give you the solution, and then you can expect that on the tutorial session after the due dates of the assignment, like on the 24th of October, we can make it like a review session for your upcoming test, just to help you, get prepared. And then your test number 1 is going to be on the 27th, right here. I'll send you more details about the coverage, etc. But you can expect that it's at least going to cover all the way until lecture 12, at least. Okay, so but I will definitely confirm a little bit more about the coverage. And the test format, let me confirm in the guide. So let's not talk too much, since I haven't really written anything just yet on the guide. Okay. All right, so please keep up with the lectures, and then you can expect the assignment to be released by the end of next Monday, and then just complete it, okay, as much as you can. And make sure you submit before the deadline to claim the credits. All right, so I would suggest today we just do the recap right away. Nothing else to announce, really. Okay, any questions about the course in general? Okay, so let's now recap about what we said last time. So last time we basically introduced more terms about the graph, but we started with this inductive proof, mathematical induction, right? It's actually quite a bit of stuff over there, but let's just recap what's really the critical steps you should really watch out for. So whenever you want to do mathematical induction, you're actually going to choose some finite quantity to really to perform the induction on. In this case, it will be the number of edges. So that means we're going to start with maybe 0, 1, 2, 3, just some base cases, and then we're going to assume by stating some inductive hypothesis. So the base cases, you just need to prove one of them, or sometimes you can prove a few to show the base cases. So that's a base case. Usually should be very straightforward to really show that it satisfies the property. And then we have to state the inductive hypothesis of certain size. Usually it could be just K, right? As long as it's beyond the base case. And then the third step would be the most creative step. It's really about to really consider something that's substantially larger. Okay? It's considering something that's substantially larger than, of course, the just K, right? So in this case, K plus 1. So please review the third step, just about the details about how we can make a graph that's strictly larger than K, which is just K plus 1, right? Just by introducing one more vertex. And the way we kind of show that is by somehow using a cloud to represent our inductive hypothesis. That's really a graph with K vertices. And now we are trying to add just one more vertex. How can we really make the connection? So there are different possibilities. In this case, we can make up to including K connections between this vertex over here and some existing vertices, right? So please follow the detail from last time. And then we're gonna somehow start with the equation here. So this will be the expanded graph. Let me just show to you. You can see expanded graph is going to be the existing one with K vertices union with just the new vertex Y. So this will be the extended graph. From there, we're going to rewrite the equation and we'll get what we want by using the inductive hypothesis. What's really important for you to check always is you must at somewhere use the inductive hypothesis to derive the final equation. That's always the case. If somehow you can simply derive the final equation without using inductive hypothesis, you're doing something wrong. Or maybe simply not something you should really even use using mathematical induction. All right, just watch out for that. So we definitely see more and more exercises about proofs as we go through properties. So today we'll see another property that can also be used, can also be justified using mathematical induction. But I think for today, in the interest of time, I'm going to assign that as exercise. We can go over the proof very briefly in the beginning on Wednesday. Today, I really want to dive deeper into the traversal. Okay, but let's now just finish off some more terms. All right, we started by talking about path and cycles, right? So path will just be alternating vertices and edges. And we talk about cycle. Cycle simply means you kind of repeat the same vertex for more than one time in the same path. And we did talk about simple cycle and also cycle, right? These two. I did make some small, maybe misleading mistake last time when I talked about these two. I'm going to clarify that in the beginning. Just bear with me. So I do have a new page just to clarify between simple cycle and also cycle that's not simple, right? These two. Bear with me. I'll show you the page a little bit later. Okay. So make sure you also review about reachable and also reachable path, right? So whenever you do a graph traversal, you can also answer many questions related to path and reachability, etc., as we'll see today. And then, so these are all the terms that we're going to learn, right? So just more like a preview. I think last time we went all the way up to over here. So today we're going to talk about forest, tree, and spanning tree. That's what we're going to do before we talk about traversal. Okay. All right, subgraph and spanning subgraph. Subgraph basically just choose a subset of the vertices and also a subset of the edges. That's it. It doesn't need to be spanning. Spanning here means the vertex must be exactly, okay, let me see, spanning subgraph. It must be exactly equal to the number of vertices. You can see here, this guy here is a subgraph. At the same time, it's also spanning because it covers all the vertices right here. Okay? So a spanning subgraph is always a subgraph, but not vice versa, because a subgraph may not be spanning, in which case it does not cover all the vertices, right? Okay, so, and also don't really get confused about spanning and also connected. Spanning is just about if you can cover all the vertices. Connection is really about between every pair of vertices, is there a path between them? So that's something just different concept. Okay, and then we simply talk about like if you think about set and subset. So every spanning subgraph is a subgraph, right? And also you can definitely find some subgraph that's actually not spanning, right? In which case, it will just be a proper subset of the vertices, right? That's something we talk about. So if I ask you in the test, if you can give me one example about a graph that's actually a subgraph but not spanning, you can easily give me that example. Okay. All right, and then we talk about connection, okay? So connection, let's read this predicate again. So if I say a graph is connected, what does that mean? That means for every pair of vertices, let me just say x and y can be a and b, it can be a and e, or it can be a and f. Any pair of the two vertices, I will be able to find x being reachable from y. A vertex will be reachable from another vertex if there's a path. For example, between a and f, I got 1 and 2, right? For example, that's one path. And I got another possible path as well. At least there's one path. I know that these two nodes are reachable to each other. Okay? So a graph being connected is you can find all the pairwise vertices. They are simply just connected. They are reachable to each other. Okay? And of course, we kind of ask this question here. Is a spanning subgraph also connected subgraph? Apparently not, because spanning is just about covering vertices. Let's say, for example, this graph over here is a spanning subgraph because we cover all the vertices, A, B, C, D, E, F. However, you can see that this particular part over here has no connection to this particular part. You can see there's no connection between B and F. There's also no connection between A and E because I'm using the pink one over here to say the edges, right? Okay, so we call that, this will be one connected components. This is just another connected components. Are we okay with this? All right, so if there's any confusion, it's now time to say it, okay? All right, so we talk about difference between spanning and connected, right? So this is spanning but not connected. When the graph is not connected, that simply means you can divide the graph into different connected components. We'll see some exercise as well. Okay, so connected component simply means it's a maximum connected subgraph. So for example, you can think about it in this way. Okay, let's make it a little bit closer. Okay, So let's look at this particular graph, right? This graph over here, you can see we got these two. This is subgraph. They are connected to each other. However, can I actually expand this particular subgraph? Somehow I cannot, because this one here is not highlighted, so there's no such edge. So I cannot really just build another edge to expand the subgraph. So this is already the maximum, so I cannot build any further. Okay? So let's see the exercise we did earlier. Okay? So if you look at this exercise we did, you can see this is a subgraph. Am I able to build or expand this subgraph any further? Because you can see I'm not able to connect this one here into any of the other subgraph. I'm not able to. And also for this one here, I'm also not able to. There's no such edge for me to connect. So this is already the maximum subgraph itself. That's the connected components. And you can see this is just another one. And then this is also just another one. So we got 3 connected components in total. Okay? And let's now think about how we can formulate this a little bit more. If I tell you that I got connected components 1 and another connected components, I got 2 of them. What does that really mean? That means if I arbitrarily pick one vertex from here, I pick another vertex from here, there is simply no path between them. Because if there was a path, I would have been able to build like a larger connected components from there, but there was no. It's already the maximum. So this must be the maximum itself already. This must be a maximum itself already as well. So I cannot really expand any further. So if you look at this path, this predicate here, right? So we say given x and y vertices, x is from here, and y is a vertex from here, and then x and y, they're simply not reachable from each other. There's no path between them. If there was one, then the connected component would be much larger, not just like what we have right now, right? All right, so that's where we were from last Wednesday. Any questions? All good? Okay. All right, let's now move on to talk about more terms. Okay, let me clarify this, right? Simple cycle and also non-simple cycle. Okay, simple cycle here. Okay, right here. So a cycle that's actually simple. First of all, it's a so-called closed path. Let's look at that exactly, right? So this will be one example of a simple path, a simple cycle, sorry. If we think about what's happening here, so we got A here, and then we got an edge to B, and then we got another edge to C. And then we got another edge back to A. Okay? It's basically a closed loop because you basically just got closed within here. You cannot really go anywhere else. It's a closed loop, closed path. And the definition goes like this. It must start and end with the same vertex. So you can see start here and also end here, A to A, A to A. And then apart from that, you don't really see any other repetition. So that'll be simple cycle. You can see apart from the beginning and the end, you can see this part over here is simply from B to C. This is itself a simple path. Okay, so in order to be a simple cycle, it must start and end with the same vertex. Okay, that's something I didn't really say very clearly last time. I think that's the example I did, but I didn't say that explicitly. So that's a clarification. What about a cycle that's not simple? Okay, so this will be one example where it's not simple. So let's see here. So I got A here, and then I go to B. Okay, A, and then I go to B, and then I go to C, and then I go back to B, and then I go back to A. Over here. Okay. Let's start with the beginning and the end. You can see the beginning and the end right here. This part here forms a cycle, which is okay. However, if you look at everything except the beginning and the end, so this part over here contains just another cycle. So that will not be simple cycle anymore. Okay, so that's not. Okay, this is not a simple path. A simple path is one that has no cycle, basically. Not a simple path. So overall, is not a simple cycle. Okay, just clarification for last time. Any questions about this? Yes?
Does this self-loop, is that considered a simple cycle or a non-simple cycle? Like it's, imagine just like one node and it loops onto itself.
The self-loop.
Yeah.
It's a good question. So that means I simply got, it's a good question. Let's say if I got this, I can double check, but let's just look at that intuitively. Let's say we got a self-loop or self-edge. So if you look at that, for example, let's say I got A here, and then I simply got that, right? So this will be as if we say A and then to A, right? Let's try to analyze that by definition. So if you look at A and A here, so these are the vertices forming the cycle. What's really the remaining path without the A and A, empty path, okay? So with the empty path here, I believe by definition is also simple path. So that would still be a simple cycle, I believe, but I can double check.
Because like when we're talking about graphs in general, like if the graph contains a self-loop, it's not considered a...
Here we just talk about path, right? It's not really about graph, so it's a bit different, right? So if you talk about graph, of course, simple graph means without any cycle. But since we talk about simple path, it's a bit different. Yeah, but I can double check this one here and then clarify next time. Again. Yes, question?
For the definition of non-simple cycle,
Uh-huh.
you said it may repeat vertices or edges. Won't they like always repeat vertices or edges?
So in order to form a cycle, right? So let me just finish this and I'll get there. Empty path is a simple path. Okay. So let's say for this one here, okay? First of all, we can see these two, the beginning and the end, it form a cycle. And then we talk about what about except for these two. But we still have a cycle here. We got a cycle within a cycle somehow. So that's not simple anymore. If somehow this, but on the other hand, this one here, if you get rid of the beginning and the end, you only got B and C left. But that one there itself contains no cycle. So that's a simple path. So that's why we said this one here is a simple one, because the cycle itself contains no further cycle. But this one here, the cycle itself contains another cycle. So it's not a simple one. Okay?
Yeah, so is there an example of a non-simple cycle that doesn't actually repeat?
That does not repeat? What do you mean does not repeat?
Because like you said, it might, like it may repeat. May repeat. Vertices or edges along the way. And this doesn't have to repeat before.
Okay, let me see the definition here. But may repeat. Well, that simply means it repeats. Okay, I see. Okay, the English problem. Okay, no problem. You know, I think I could be confused too, but gotta repeat in order to make it not simple. Good. Good to be picky. Good. Any other questions about this? Good. Okay. I'll double check the slide. If there's any confusion there, I'll fix the slide as well. But that's the definition go with. All right. All right. Let's now talk about new terms. Let's start with forest and trees. Okay. So let's now take a look at that. So we are basically starting from slide number 20. But let me just go with the iPad, right? Just to give you some definition here. Okay. What's really a forest? Okay. Forest by definition goes like this. Okay, a forest is basically an undirected graph, undirected, and also no cycle. And usually a graph with no cycle we'll say is acyclic. Okay, acyclic. Of course, with a cycle, it's called cyclic, right? So just A over there. Just watch out the spelling there. All right, that's really forest. But let's see one example. This is a forest right here, right? So here you can see that it's undirected, right? You can see there's no direction of the arrows. And there's no cycle, right? You can see there's no cycle here. And there's an important property over here. Okay, I'll write it down. It's also on your slides. When you say it's a cyclic, just for this part here, when you say it's a cyclic over here, it says that any two vertices are connected by at most one path. Okay, let's now, that's the definition, right? Being a cyclic. Any two vertices. So now when we say at most one, okay, that means less than or equal to 1, right? Let's think about what if it's not at most 1. That means at least 2. Agree? Okay. And then from here, let's think about what if at least 2 edges connecting two vertices. If you actually got this one here, which is negation of at most 1, that means you got at least 1 cycle. How can you think of it, right? Very easy to visualize. Let's say if I have 2 vertices, let's say V here, and also I have another vertex U, right? Any 2 vertices. So why don't we say it's simply V and U, okay? And then we're saying that somehow these 2 vertices are being connected by at least 2 vertices. At least 2. Okay, at least 2. Or larger than 1. You can think either way, right? I just want to get a negation of less than or equal to 1. Or you can say it's larger than 1. Okay, the same. If there are at least 2 paths, you can think about there is somehow one path going here. Of course, there might be many different vertices along the way. I'm just making it a little bit more abstract, right? So from here, from V here, I can somehow get connected to U. I can follow another path. So you can think about this as path number 1, which will start by V and end with U. I can have another path that can also start by V and also end with U. This will be path number 2. If I have this, I do have a cycle. Agree? Right? Because visually, obviously, you can just go all the V all the way to U and U all the way back to V. So it's a cycle, obviously, right? Okay, so in this way, there's a cycle. Cycle from, for example, V to V. Whether the cycle is actually simple or not simple, we don't know, because we don't know if there's any nested cycle, which we don't need to know in this case. All right, so when you see that at most 1 on the slide, so that's actually how you understand it. All right, so that's about a forest. Another thing to also consider, okay, when we say at most 1, that means less than or equal to 1, okay? When 2 vertices is connected by exactly just 1 edge, that's kind of straightforward. Maybe they're just connected. But what if they are not connected? At most 1. Okay, so here, think about some special case. If U and V are connected by 0 edge. You can think about 0 is like a special case for at most 1, right? Less than or equal to 1. So I'm just talking about 0. Okay? So the 0 here is a special case. Special case of less than or equal to 1. If you can actually find such 2 vertices in the graph where there are not somehow any path between them, so that means the whole graph is not connected, because at least these 2 vertices are not connected to each other. Okay, so this would mean the graph is not connected. So the important conclusion is the forest, by definition, a forest may or may not be connected. Connectivity is not a requirement for forest. That's the main point. All right? So you can see just by this particular sentence over here, we can already kind of derive to say forest does not need to be connected. It's not a requirement. Okay? May or may not. I'm going to summarize many terms in a table in just one moment. Let's introduce some more terms. Okay? All right, so let's talk about the next one. Okay? Tree. Okay? We got forest, now we also got tree. Okay? So let's say this. Let me just copy this one here. Okay? I'm running out of space. Just make sure. Okay, good. Okay. Let's talk about something called trees. The definition of a tree is this. A connected forest. It's a simple definition. Remember we said earlier, forest may or may not be connected. However, in the case of tree, we want it to be connected. Once you see this definition here, you can draw some relation right away. Okay? So think about, you got some forest. These are all the possible forests. And then you think about, so these are all the possible trees. So what would be some forest that's not a tree? It's really about being connected or not, really. Okay? A forest that is not connected. All right? So we said earlier, this one here is actually a forest, right? This one here. Okay, let me just make it explicit. So think about this is one example where it is a forest, but not a tree. Because it's not connected, so it's not a tree. Let's copy this diagram here to see how we can make it a tree. Let's see. There are different ways to make it a tree. Okay, for example, I'll show you maybe two ways. Okay, so one way would be, let's say here we can add some edge. If we add between E and F, as soon as we have added this particular edge, it will be a tree. Agree? Because now every node is connected to each other. So this will be a tree. So this is one example of a tree. Okay, let's see another one. Okay, or I can try to connect, for example, these two, E to D, right? In that way, that's also a tree. So this is also a tree. Okay. And question for you. Okay, let me just make one more copy to make one more point. So let me make this one a bit smaller. Okay. Okay, right here. Okay. Okay, one more copy here. Okay, maybe. Okay, still visible. All right, so forest over here. Let me now try to give you one example here. Tell me if that's a tree or not. It's connected for sure. What if I try this? This one here, and this one here. First of all, it is connected. Do we agree? This one definitely is connected. Because if you try between every two vertices, there's always a path. However, is this a tree? Why is that not a tree? This is a cycle. Remember, a tree is a connected forest. But this one here contains a cycle. It's not even a forest. All right? All right. However, this one is cyclic. So that means it's not a forest. And by definition, if that's not a forest, it is no way it's a tree. Okay, just remember. Okay? Connectivity is very important in order to be a tree, but also remember it cannot be cyclic. That's so important. Otherwise, you wouldn't be even a forest in the first place. Okay? All right. Let's do one more turn, and then we can do some table to summarize many things. Okay? Let's do one more. Okay? And final term here is called spanning tree. Okay? You may have heard about a term called minimum spanning tree. It's kind of related, but we'll get to the minimum part a little bit later when we talk about the algorithm. Okay? Spanning tree. By definition, spanning tree is like this. I'll give you two possible definitions. The first one a little bit more verbose. Spanning tree. Okay? A connected spanning subgraph that has no cycle. Okay? Connected spanning subgraph that has no cycle. That's one definition. All right? And then another way to see that is a spanning subgraph. That is also a tree. All right? So you can think about in both definitions here, I'm really using the term spanning subgraph right here, right? However, you can see that in the first definition there, I say connected and also no cycle. Right? That's exactly the essence for a tree. Right? Exactly what a tree is. So these two definitions are equivalent to each other, but you should really know both. All right? Okay, and let's now try to see some example for spanning tree. Of course, later on we're going to learn about how you can compute some algorithm to really, to get a spanning tree or minimum spanning tree from some graph. But we'll get that a little bit later, maybe after the reading week. Okay, let's see this. Let's say this is our graph, right? Let's now try to see, there are 5 different possible spanning trees in this particular example. Okay, let's see what we have. Okay, of course, in order to be a spanning tree, it got to be spanning, and also it got to be a tree, no cycle, and also got to be connected. Okay, let's see. So let me just use just the dash line over here simply means no edge. So let me draw the edge, right? Give you 5 different spanning trees. The first one, I can say I got between A and B, A and E, and also A and C, right? First of all, let's get all these 4 nodes connected. I still got F and D not connected, right? So one way to do it is go to F and go to D. Notice that no cycle connected. Okay? Let's say I still got AB, AE, and also AC connected in this way. Okay? Now, in order for me to get to F and D, I can say, for example, I can go this way, go to F over here, and then for D, from F to D. I still have no cycle. Right? Okay, another one. Let's say I still got AB, and also AE, and also AC. So now I can try to connect F and D in this way. I can say I want to go to the D first, and then for F, I can go through D. So this is another spanning tree. Right? And another two. I can say I connect AC and also AE, and then ED, this, or this. This one here. All right? Okay, final one. I can do this one here, and then I can, from D, I can connect to F, I can connect to C, And then from F, I can go to B. That's another spanning tree. Okay? One thing that's actually quite important, right? You can see I got 5 different spanning tree. You can think about spanning tree number 1, spanning tree number 2, spanning tree number 3, spanning tree number 4, and spanning tree number 5. They actually share one property in common in terms of the number of edges and vertices. Okay? So let's say for this particular graph, let's see. The number of vertices will be 1, 2, 3, 4, 5, 6. The number of edges will be, let's see, 1, 2, 3, 4, 5, 6, 7. Okay? The potential edges, okay? So let me take potential. Maximum. You know what? Let me not confuse you over here. So I think it'd be better, let me not mention this. Okay, sorry. Let's now, vertices for each one of them will be spanning, so it's exactly just equal to 6. Okay, 1, 2, 3, 4, 5, 6, all the same. Let's count the number of edges. It turned out it will be the same for each one of them. Number of edges, you can see for this one here, it's going to be 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And also 1, 2, 3, 4, 5. Okay? 1, 2, 3, 4, 5. And this one here, 1, 2, 3, 4, 5. There's no coincidence. There's actually one property. If you got a graph that happened to be a spanning tree, the number of edges will be exactly equal to the number of vertices minus 1. It's a property we can actually prove. Okay? Is equal to 5, which is equal to the number of vertices minus 1. So let me write this relationship over here, but we're going to see that as a property anyway later. Okay? G is a spanning tree. Implies the number of edges equals the number of vertices minus 1. Okay? Is one of the properties we're going to see a little bit later. Okay? Okay. All right, before we do the exercise, why don't we try to summarize about the terms we have seen so far? I think that'll be nice. That'll be useful for your study. Okay, let's see this. Okay. Let's have a summary. Okay. Okay, summary of the terms so far. Okay, so let's now do the following. So far we actually got quite many terms. Okay, let me just try to be careful with the space. Okay, so here, and also we got here. So let's say we're gonna have different criteria to to compare. So one is about whether or not the graph is undirected. Yes or no? And then we got something called whether or not it's acyclic, contains no cycle. And then the next one, whether or not the graph is connected. And the final one, whether or not the graph is spanning. Okay, so these are the different criteria we can actually look at, right? So let's see the terms we have seen so far. Let's start with the most general one, somehow. Let's say in the sequence of our introduction. Let's first of all start with subgraph. Okay, and then we have spanning subgraph. And the next one, we have forest. okay, which we just covered today. And also we have tree. And then after this, we have spanning tree. Okay, we got 1, 2, 3, 4, 5. 5 different terms. All right. So for each one of them, you can think about whether you're going to check if the criterion is necessary. If the criterion is not part of the requirement, you can put a question mark to say you may or may not satisfy that criterion. Okay? Why don't we take a very short break? You can feel free to fill out the table during the break. Otherwise, I'm going to do it maybe after the break. Okay? Why don't we take attendance by taking a short break as well? All right, let's now try to fill out the table here. Okay? I think just for the first one, undirected. I think for our context, we just assume our graph are actually undirected. There will be certain special graph we're going to assume it's actually directed. But for now, let's assume everything is undirected. So I'm just going to check. 1, 2, 3, 4, 5. Okay, so undirected is not really the issue, focus point. Let's see acyclic. Okay. So let's see subgraph. Does a subgraph need to be acyclic? Not really, right? As long as you got sub-edges and sub-vertices, you should be okay, right? So for this one here, I'll put a question mark, which means it may be acyclic or maybe not. Okay, that's what question mark here. May or may not. Maybe, maybe not. Okay, that's what it really means. Okay, and then for spanning subgraph, also whether or not the spanning subgraph contains a cycle doesn't really matter as long as it's spanning. Right? So this one here, also question mark. All right? What about forest? Gotta be acyclic, right? That's really one of the essential criteria. Okay? Forest must be acyclic, no cycle. A tree is a special case for forest. Of course, there's no cycle. Spanning tree is even a special case for tree. Of course, no cycle. All right? All right, let's now talk about connectivity. Okay, for subgraph, again, it's a very general concept, right? Whether or not the subgraph is actually connected or not, we don't care, right? May or may not be. And spanning subgraph. So we already talked about spanning and also connectivity, right? So these are two independent dimensions. So again, we don't really know. You cannot really say, given that something is spanning, it must be connected. Not really. Right? There's no formal relation between the two. So also may or may not be. Okay, forest. Does forest need to be connected? Not really. Only the tree need to be connected, right? Okay. So forest, not really. Okay. For the tree, yes, it has to be connected. And spanning tree also needs to be connected. All right. So finally, subgraph doesn't need to be connected. Spanning subgraph doesn't need to be spanning. Of course, by the name, right? That one's obvious. Okay, good. How about forest? Not really. You can look back to the definition. It doesn't need to be spanning. It just need to be, let's see the definition here. I can look back, but I can tell you this one here. I don't think it's spanning. Doesn't need to be. And for the tree, also doesn't need to be spanning. But for the spanning tree, this one here need to be spanning. Okay, so maybe for these two, just double check. Okay, it is the case. Okay, forest and tree do not need to be spanning. So that's why we got a special case where we say spanning tree. It got to be a spanning and also got to be a tree. Okay. All right, so that's the table. Some simple stuff just to summarize about what we have learned so far. All right, so let's now do the next one. Okay, quick exercise. Okay, that's also on your slides. Let's say this is a graph. And we're kind of asking which one is a spanning tree of the graph. Which one? Could be multiple choices. That's correct. Well, none of them is correct. C? Okay, I agree. First of all, it is spanning because 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. It's definitely spanning. It's a tree because you can see somehow it's connected, right? And also there's no cycle, right? Obviously, that should be C. That's good. But let's talk about why A is not a spanning tree. What's wrong with A? Cyclic. Yeah, it has a cycle, right? This one here, it is spanning. But it is cyclic. Okay, so that's important. All right. How about B here? Not spanning, right? It's not, there's no cycle, but it's not spanning. This one here is acyclic, which is good, but not spanning. Okay, just more like a visual example. Okay, okay, good. Okay. Okay, we got some property over here. I would suggest, let me delay this example here maybe to the beginning on Wednesday. Let me go over this maybe as the first thing on Wednesday. I would just like to go to traversal right now, right away, just to see some traversal before. We got about half an hour. I think we can cover some traversal nicely. Okay, I'll get to this one here on Wednesday. Okay, let's talk about traversal. All right, so that will be starting from slide number 24. Okay. By definition, what's really a traversal? So the definition is very similar to how we define like a tree traversal. So what's really a tree traversal? It's just a systematic way to really go over all the nodes in a tree. And of course, what we learned from 2101, we got how many different traversals? Pre-order, in order, and post-order, right? And which one of them is more restrictive, if you recall, from the tree traversal? We got pre-order, in order, and post-order. Which one has some restricted context you can apply? In order, it has to be a binary tree, right? Okay, quick review. Okay, so now let's talk about graph traversal. Okay, so graph traversal, basically we'll mainly just talk about depth first search and also breadth first search. So these are the most common systematic way to go over the vertices and edges. But today we'll only talk about depth first search. Okay. Okay, systematic way, and then you gotta examine all the vertices and edges. So in 2101, when we do tree traversal, we didn't really emphasize about edges, but in the graph, we have to talk about, you have to somehow cover all the vertices and edges. Okay, so that's important. Okay. And okay, what's really efficient? Okay. So efficient here, I'll just mention about the running time. That's something we'll see a little bit later when we see the algorithm. But in order for the traversal to be efficient, right, it's going to be linear on the number of vertices and also the number of edges. Okay, so this might be the first time you're seeing that we're somehow combining the inputs having two components, right? So this will be the number of vertices and also the number of edges. So you can see the V here is about 1, 2, 3, 4, 5. The number of edges will be 1, 2, 3, 4, 5, 6, 7, right? So these are two different measures. And we're saying that in order for your traversal to be efficient, it's got to be linear upon them. Cannot be, for example, square. Cannot be quadratic. Cannot be. Okay. And then, so there are different applications for the graph traversal. Okay, let's just see some of them. We'll just go over them very quickly. Okay, and then we'll see the actual depth first search. Okay. So let's say this is the graph you're given. So after the depth first search, which we're going to talk about, you can think about after. So let's say we're given this input graph. You can think about after the depth first search. The graph is actually going to be annotated somehow for the vertices and also edges. So after the depth first search, all the nodes, all the vertices will have been visited. Okay, so I will simply say visited. Okay, I will use green to say visited, all of them. Okay, so green one here simply means all the vertices have been visited. Okay, all of them. And for the edges, we also need to make sure we cover all of them. But in the case of the depth first search, you can somehow cover the edges in two different ways. So that's something we'll also see. I'll just give you some idea quickly, just a first example, right? It turns out, in this particular graph, if we do the depth first search, one possible outcome can be, we're gonna color, okay? Let me color them first, and then I'll talk about, okay? We can color this way. So these are the edges right here, okay? So somehow this can form a spanning tree, just happen to be, right? So the pink one over here are so-called discovery edges. Discovery edges. On the other hand, the remaining edges are called the back edges. So C to A, D to A, and also E to A, right? Lighter green. These are called the back edges. So exactly how we can mark the vertices as visited or not visited, and also the edges as either discovery or back edges, we're going to see. There will be some algorithm we have to go through. Okay, we'll talk about it. Okay. Okay, so we got some applications over here. So let me also skip this one just for now. So once we see some example for the traversals, we can actually revisit this. That'll be revisit this to make a little bit more sense. Okay, so visit a little bit later. Okay, I'll come back later. Okay. Okay, let's now go to depth first search. Okay, let's see that. So this part over here is from your slides. So let's go over that carefully, okay? We don't really see any algorithm over here. We just see some principle about doing that. So we'll try to master how to do depth first search visually first, and then we get to the code later, okay? Okay, a depth first search. And given some graph, arbitrary graph. So the graph just got vertices and edges, okay? Let's say this is the graph. And the graph happened to be a tree, just in this case, right? Just as a first example. And then, so we got to start the depth first search from some vertex, starting vertex. Let's say we start with some vertex. Let's say we start with A, for example. Starting from some vertex, for example, it could be A. So this would be the starting point of the depth first search, let's say. So what we are trying to do is we are trying to build a path for as long as possible from A, along a path from V. And let's see the three different principles over here. Okay? So principle number one. The path is constructed by following an incident edge. Okay? So here, notice that an incident edge. For example, let's see. When we start from A, over here, how many incident edges does A have? 1, 2, and 3, because degree is 3, right? So that means from A over here, you can choose to either go to here, or here, or here. You have choices. It's kind of arbitrary, okay? But in the actual algorithm, maybe somehow you store, maybe the neighbors of all the adjacent vertices B, C, and D in a list, in which case you just go from the beginning until the end, right? So N here is kind of arbitrary choice. So if you actually choose to first go from A to B, you're going to have one particular traversal. But if you go from A to C, you might have another one. If you go from A to D, you might have another one, right? So it depends. Just in general, okay? Okay, you're going to start from some incident edge. And then you will try to extend the path for as far as possible. The path is extended as far as possible, okay? Until all the incident edges will only lead to everything that has been visited already. Okay, so let's say, for example, just in general. So if I got some vertex V over here, okay, let's say I may have something before me, okay, maybe this is somewhere in the middle of the graph, okay. Let's say now I actually got 3 incident edges. So maybe I got one neighbor and another neighbor and also another neighbor. Let's say X, Y, and Z over here, okay? If any one of them is actually unvisited, I should be able to extend the path by going there. But in the extreme case, if all the 3 vertices have been visited already, I cannot really go any further, okay? So let's say all these neighbors have been visited. In that case, the path cannot be extended any further. In that way, we should really do something called backtrack, okay, which we'll also see. In that case, you should really backtrack. Okay, we'll see some example as well, okay? Yeah, if you cannot extend any further, you're going to do something called backtrack. All right? Oh, and then we'll just see example here. Let's see here. If you have a, let me just give you the answer to these 2 questions first, okay? What kind of data structure should we use usually for depth first search? Okay, so stack. Depth first search is very naturally to be implemented recursively. So to really simulate recursion, you can also use a stack. But we're going to see how we can use a stack in just one moment. Okay, stack. And if you recall from 2101, it's last in, first out. Level stack. Okay, let's now see what we can do. Okay, let's make some assumption. Let's say the order in which you're going to go for the neighbors, you will follow them alphabetically. Meaning that, so here, from A here, I can either go to B or C or D. Alphabetically, I should really go to B first, right? And then C and then D. So that'll be the order. Okay, let's make the assumption. So the assumption is we're actually going to iterate through the neighbors alphabetically. Okay, let's say. And we also try to label the order of visiting the nodes. So let's say we start with, in the beginning, all the nodes are unvisited in the beginning. So let's say the red over here simply means they're all unvisited. Okay, let me see better. A, B, C, D, E, F, G, and H. We start with this, first of all. Okay? And then we start with A. So that means A right now is now visited. So we can change that to be visited. So we change its color. Of course, programmatically, you can change the Boolean flag from visited into unvisited, like a true to false. So here, I'm going to, okay, I'm going to change that to visited right here. And then I follow my assumption. I'm actually going to go to B first. You can think about here, I can either go to, if I go to B, that means I go to some unvisited nodes, which is the right way to go. Right? I go to somewhere where I haven't really visited yet. Okay? So I'm just going to go this way. Okay, let me just call it that as pink right here. Okay? So this will be the first one I visited. Let me also use a stack along the way. Okay, so I start with A. And then by following that edge, I will go to B. As soon as I go to B, I know that B has now been visited. Right here. Okay, 2 over here. And then now for B, I have a choice. I can either go to E or F. Let's follow the assumption. We'll go alphabetically. So go to E. So go right here. And then we go to E. E over here. And E will now be visited. Okay, so far so good. Basically, you want to go with this for as long as you can. You will actually see that we'll hit some bottleneck very soon. All right? So let's now go further. So now for E, we have a choice. Either go to G or H. G or H. Alphabetically, we'll go to G. So we go here, go to G here. So that means number 4, we got G on the stack. Okay, that'll be active. And then we're just going to change G from unvisited to visited. Right here. Okay, so far so good. And for G here, you want to go for all the edges that have not been marked. So far you can see all the pink ones. They are the marked edges. We call them the discovery edges, meaning that from here, I simply go somewhere that used to be unvisited. It's called discovery. And from B here, when I go to E, I also discover something that has not been visited before. So it's called discovery edges. Okay. So let me just use, so the pink one over here is something called discovery edges. Discovery edges. Okay, so we cover actually one kind of edges already. Whenever you go from one vertex into another unvisited vertex, it's called discovery edges always. Okay, so now for G here, we have nowhere to go. We cannot say go from G to E, simply because this edge is already marked as discovery. We cannot go there anymore. We don't go there. It's nothing that's unmarked. In that way, G here should be popped off from the stack. All right? That means we go to E. So E here, right here, we go to any of the unmarked edges. This will be 1. Agree? Okay? So we go for another discovery edges from E to H. So this one here is going to be number 5. That's going to be H right here. So that one is going to turn H from unvisited into visited. So now H is now the top of the stack. So now let's look at where can we go from H. From H, we only got one edge, but this one has already been marked. There's nothing that's unmarked. So H should also be removed from the stack. So now the top of the stack will be E. And we'll go to E here. Is there anything else we can go from E? Not really, right? You can see we got 1, 2, and 3 edges. But all of them have been marked as discovery. There's nothing that's unmarked. So we also remove E as well. And we go to B. B here, the only thing that's unmarked is to F, right? So we actually go here. And then that one there should be number 6. Okay. And then we simply change F from unvisited into visited. Okay, so let's put F on the stack. Okay, F. So F, do we have a choice? We don't, because the only incident edge over here is already marked, nothing that's unmarked. So we got to remove it from the stack. All right, and then we backtrack to B. So B here, you can see all the incident edges have been marked already. So B is done. So B should be taken away. All right, and then we go to A. A is the only thing that's left in the stack. All right? So for A here, so you can see just by going this way here, we got all these traversal done in the subtree. Right? So now we just got to go to the next one. We're going to go alphabetically, so go for this one here to go to C. So over there, we're just going to go to C. Okay, so that one there is going to be number 7. Okay, and that one there is going to turn C from unvisited into visited. And we're going to push C onto the top of the stack, right? And for C here, no choice because the only incident edge is to A, and this edge has already been marked as discovery, right? So we don't have a choice, so we got to remove C from the stack. All right, and then we go back to A. And for A here, you can see for A, these two are marked. The only thing that's unmarked is right here. So we're going to go there, another discovery. Okay, and then this one here is going to be number 8. And for that one, we turn this one here from unvisited into visited. So we push D to the stack. All right. And for D here, we have no choice, right? The only edge is already marked. Okay, so we're going to remove D from the stack. From there, and then we got A. A, you can see we have already visited all the neighbors. So A is also done. Remove it from the stack, and the stack is empty. So that's done. So this is actually a very special case for graph traversal because the graph that's given is a tree. There's no cycle. But later on, we're going to see there's another kind of edge which we'll see, which is called back edge. But we don't see that in this example. Just to start simple, we only see discovery edges. Okay, so the graph is a tree. DFS marks discovery edges only. Okay? Discovery edges. Any questions about this first example here? Right? So somehow this first example just show you the discovery edges, simple enough, right? But we're going to see back edges as well in the later example. We're going to do that very soon. All right? And question for you. Based on the order, right? You can see, turns out the order is 1, 2, 3, 4, 5, 6, 7, 8. What kind of tree order traversal does it correspond to? Pre-order, okay? Because somehow you go with the parents before you go for the child. Question?
I don't think the number quite corresponds to pre. Wouldn't pre be like G, H, E, F, B, C, D, A?
No, you always go for the parents before you go for the child, right? Before you go for the subtree, right? That's pre-order. I'll put it down here, okay? Maybe we should really revisit maybe some pre-order traversal next time. So just to see, but it's really pre-order. It's a special case, right? Okay, so we can do some more example next time, but it's a pre-order. And remember pre-order is parent first. Children next. Okay, we can do maybe one or two examples to start with as well on Wednesday. Okay, it's really pre-order. I'm not saying depth first search always corresponds to pre-order because this is only the special case where you actually got a tree. All right, let's now see quickly about marking the vertices and edges, and we might just be able to do one more example. We'll see. Okay. All right, so this is another set of principles that we got to follow for depth first search, but we already covered quite a bit of them already in that first example. Okay, so when you talk about marking the vertices, is either vertices will either be unvisited or visited. So in the very beginning, when you first start with the depth first search, everything will be unvisited. Okay, Everything is unvisited. You can think about here, all vertices unvisited. Also, all edges unmarked. Or you can see another term, unexplored. Okay? So here you can see the edge is there, but I didn't really give it a category, either discovery or back edge, right? That's in the beginning, right before the depth first search starts. And we're going to see different scenarios, right? So that's something we're going to go over, but I'll let you maybe read it, maybe when you study for that. Let's see just two cases. Discovery edge, we already said. Okay? Let's say, for example. So let's say, for example, let's say A, B, C, D, E. In the beginning, everything is unvisited. And we start with A. So we change this one here from unvisited into visited. And let's say if we choose to go for this particular neighbor. So this will be a discovery edge, which will turn the neighbor B from unvisited into visited. Okay? So that's called a discovery edge. Okay? Discovery edge. It's basically discovering something that used to be unvisited. Discovering a vertex that is unvisited. Back edge. Okay, I'll just give you one example, and then we're going to do just partially the example. Let's say, for example, let's say I got this view to start with. A has been already visited, and B has been already visited, and C also has been already visited. I also got two discovery edges. A discover B, and also B discover C. Okay, so far so good. I got two discovery edges so far. So now, from C over here, how many choices do I have? The choices I have are those edges that have not been marked yet. Only this one has been marked. So I can either go this way here, I can go this way, I can also go this way, right? So now let's say if I go this way here, in that way, I will be going to some vertex that has already been visited. That's not something we saw ever in this particular example, right? So when you study that, just notice that there's no back edge in this very first example. But in this example here, see here, if I go for this particular unmarked edge, I will go to some vertex that has already been visited. So that's something called a back edge. Okay. So this one here, let me just draw that. Okay, so this one here. Okay. So this one, let me just write it down. So this is from C to A. We basically leading to vertex A that's already visited. That's already visited, and it's called a back edge. And whenever you have a back edge, that means you have a cycle. Okay? That's something we'll see later as well about a property. Okay, so when you have a back edge over here, that means the graph is acyclic. Sorry, the graph is cyclic. I beg your pardon. The graph is cyclic. Because if you think about from here to here, we basically got one possible path from A to C. And then here we see there's another possible path from C to A. You got more than one path between two nodes. And we said that means it's a cycle. All right? All right, we're pretty much running out of time, but next time when we start with, I'm also going to talk about, just run different example about that first search. So the plan for Wednesday, we're going to go over some pre-order traversal. We do that property check, property proof as well, and also do that first search. I'm also hoping to talk about a little bit about Java implementation for Graph. Okay, that's the plan. All right, thank you, and then I'll see you on Wednesday.